Okay, a couple issues. So I think some of you noticed on the syllabus that I use this remind system. Some of you may have used it in high school. There are instructions on the syllabus on how to join that. Usually what I do, so instead of sending out email to the class, especially for notifications, if I'm going to be sick, I typically use that instead of sending out an email, because students don't check their email, I found. So with that system, you can choose to either get the notifications by email if you want, or by text message, or if you install the app, you can get notifications. So it's your choice, but I usually just use that. I don't use it often, maybe once or twice over the course of the semesters. I'm not going to flood you with messages, but it would typically be, something comes up and, I can't be here, then, I use that to let you know. Or, so there's actually, it's probably more important for my EMAG class at 8 o'clock in the morning that I let you know as soon as possible, or you guys find out as soon as possible than it is at 3 o'clock in the afternoon. But actually there's two groups. I have one per class, and then one I use if I'm canceling all classes, I'll just send out a message for that. That's what I use. So if you could join that group, you have to actually join. I can't sign you up. The other thing is I sent out a message about tutoring for this class. Someone pointed out it's the same time as the 3:54 tutoring session. I'm not sure that that's a problem. It may be. They're both 2 hours long, so if they're not actually additional instruction, the tutors are there to help you with the homework. So, one's down here, one's upstairs. So you could come here, if they're busy upstairs, whatever. I did send an email to Lynn, though, asking her if she could move to Thursday, but since the homework is due on Friday, it might be more beneficial for you to have the tutoring session on Thursday evening instead of Tuesday, but I haven't gotten a response back from her. So if she's agreeable, we'll move the tutoring session for this class to Thursday evenings. If not, I think we'll just keep it on Tuesday and see how things work out. I think I mentioned last time I had posted some short video. I think both of them are under 5 minutes long on how to install Octave. Did anyone run into any issues with that? That meaning that you didn't even try it, so there are no issues, or?
I already had it.
You already had it, okay. So let me know if there are issues. It's fairly, I think, straightforward. The installation is pretty easy. I want to actually show you how, at the end of the lecture today, to get started with Octave to write a simple script. In my opinion, it's really easy to use. Our first exam is actually 1 week from Monday, so it's hard to believe that we're coming up on the first exam. But I give the first exam after, I guess it's, I have to look in the syllabus. Is it just chapters 1 and 2? It is. Okay. Let's see. The handout I gave you on convolution, that's from tables in the text. I've extended it a little bit. Okay, I think there is some additional convolution. So there's convolution properties on one side, and then there are some convolution pairs on the other side. I think I extended the convolution pairs table. It's got a few more pairs than the corresponding table in the text. I find it more convenient, especially when you're working on homework, to have a separate handout instead of flipping back and forth between the text and the text. So I want to briefly go over these convolution properties, and then we'll look at how to, with the properties, you can, save yourself a lot of work. I do want to try and go through one more example as well of actually calculating, going through the convolution using the integral. But the commutative property, what that really means is, I'm going to show block diagrams for everything. That, you know, if y of t is equal to x of t convolved with h of t, we can get the same output if I actually created a system whose impulse response was x of t, and then I fed it the impulse response of this system. That would give me exactly the same output. So h of t convolved with x of t is equal to x of t convolved with h of t. The associative property actually means that if I've got h1 of t and then run that output through a second system, to produce y of t. So I could call the output of my first system w of t, but it's a time domain signal. It's another signal that I could then convolve with the second system to get my overall output. But the associative property means that I can actually, well, it means two things. It means I could swap the order. And get the same output. Okay. And then it also means that I could combine, if I could find a system whose impulse response was equal to the convolution of the two impulse responses. That also is equivalent. Again, the restrictions here, this is for linear time invariant systems. Okay, these properties don't apply to nonlinear systems or non-time invariant systems. But you know, so for a linear time invariant system, you know, I can run my input signal through one circuit, take that output, run it through a second circuit. And what this says is I can swap those two circuits and still get the same output. The distributive property just says it distributes across a sum. So if I have this input x, which I feed into two systems, h1 of t and h2 of t, and then take those two outputs and then add them together to produce my overall output. That's equivalent to, by the distributive property, taking x of t and running it through some system whose impulse response is the sum of the two impulse responses. I'll get the same output. Now, a good question would be, you know, how do we design a system that has a particular impulse response? That's not one we'll actually tackle in this course. Okay, that's actually filter design or system design, so that we'll see it's equivalent to actually designing a circuit that has a desired frequency response, because there's a direct correspondence between the impulse response and the frequency response of the system. That's a filter design issue. The time shift one is a really useful one. Okay, it basically says that if I delay the impulse response, that delays the output. Or if I delay the input, that delays the output. But the total delay is the delay in the impulse response plus the delay in the input signal. So, some pictures, let's say that a x of t looks like this. And let's say h of t looks like this. I'm going to make it exactly the same. Now, I don't know, this is, we'll see how to get this. This is probably in this table. May be able to get it from the table. Actually, convolving 2 unit steps. Because this is a difference of 2 unit steps. This is a difference of 2 unit steps. So I can expand all that. This convolution, y of t in this particular case, y of t turns out to look like this. 2t, t, 0. And then those overlap, it would have a height of t. The area of the product would be t, which is the height. So, and you'll probably verify this in one of the homework problems, that this is the result. I'm not worried about what the actual, getting that right now. I'm really concerned, you know, what does the time shifting property mean? Okay. So, and you can think about, of course, this is a response to an impulse. Here, x of t, you can think of it as, you know, just the sum of impulses, one arriving at t equal to 0, and so I start getting a response at t equal to 0 because my impulse response starts at t equal to 0. But the last impulse here is at time capital T, so it produces another impulse response that's going to last for another capital T seconds after that. That's why this thing extends out to 2t. Regardless of that, what the time shifting property says is, I could say, what's the response? Let's say I have this new input, which is my previous input delayed by 2 seconds, right? It's just right shifted by 2 seconds. What am I going to get now when I convolve this with that? I have to going to go through that whole convolution, that interval process. And the answer is no. This input is that input delayed by 2 seconds, so my output is just going to be delayed by 2 seconds. So that means the corresponding output here would be 2 plus t, 2 plus 2t. Still have the same height. This is the corresponding y of t for that impulse response. And similarly, if, you know, if an impulse at t equal to 0, you know, my h of t didn't actually start until 1 second later. That means even if my input starts at 0, I'm not gonna get output until 1 second later. So the total delay is, you know, the overall delays in both the x of t and h of t. So again, I don't have to redo this problem if I see that this input or the impulse response is just a shifted version of a previous result. Convolving with an impulse gives me that same function of time. And it's probably best, you know, certainly convolving with h of t has to give me h of t. Because when I convolve with h of t, you know, that means when I convolve delta t with h of t, I'm asking, well, what's the output of my system when the input is delta t? By definition, that's h of t. But that's true for, you know, applying the properties of the impulse that we looked at previously. You can show that this is true in the convolution interval. A little more useful is that if I convolve with a shifted impulse, that just shifts the function in time. Right? So some useful properties to remember. convolving with the unit step. What that actually gives me is x of tau d tau. This is our integrator, ideal integrator. So convolving any function with the unit step actually gives me the integral of that function. And again, I can think about convolution as a mathematical operation involving a time reversal and shifting and integration of the product. Or I can think about it as, what happens from a systems approach. If one function is h of t, I can think about that as being the impulse response of my system or circuit. And then the other function is the input, then convolution gives me the output. The final property is this width, and the width of y of t is equal to the width of x of t plus the width of h of t. Again, that's a good check on your convolution homework. You see that here. Okay. This has a duration of t or a width of t. This has a width of t. So y of t, the result from convolving the two should be 2t. Okay. Shifting it doesn't change the width. This still has a width of t. So the output should still have a width of 2t. Okay, so this is a problem from the textbook. And but here you're asked to use, or you can use, the properties of convolution, so that you actually don't have to evaluate the convolution integral. So by the distributive property, this convolution distributes over a sum. U of t convolved with delta t, though, is what? Okay. It's just U of t. And so what is convolving with delta t minus 1 do? That delays by 1. Okay. And it's multiplied by minus 3, so this is U of t minus 1. And then plus 2 U of t minus 2. We should be able to sketch that. Okay, U of t would start here and go forever. And then at t equal to 1, we're going to subtract 3. So we'll go down, if I left myself enough room, but this will go down to minus 2. So I'm going to do this. And then that would go on forever. But at t equal to 2, we add 2, we're at minus 2. That'll bring us back up, and then that will continue forever. So convolving U of t with that sum of 3 shifted impulses would give us that result, a result that looked like that. This is the mathematical expression. If t is U of t convolved with 2 U of t minus 2 U of t minus 3. Okay. So what's U of t convolved with U of t? I think that one's on your convolution table. It's the first pair in table 2.2. Right? U of t convolved with U of t is actually tu of t, which is also our ramp function. But this is 2t u of t. And then here we've got u of t convolved with a delayed unit step. Okay, so we're going to use our shifting property. U of t convolved with u of t is t u of t, but now I just delay that by 3 t minus 3 u of t minus 3. I could also write that as 2 r of t minus 2 r of t minus 3. That's equivalent. And then, you know, quick sketch of that. 0, t, 1, 2, 3. So r of t kicks in right here at 0. It would normally have a unit slope, but it's multiplied by 2. So at 1, it's going to be 2. At 2, it'd be 4. At 3, it's actually going to be 6. And then this next one kicks in. What's going to happen after that? And it's going to be flat line, but stay at 6. Now, this is actually a pulse. You know, the 2u of t minus 2u of t minus 3, that's a pulse. But it's convolved with actually a unit step, which has infinite duration. So the output in this case has infinite duration. So the width property still applies, but in this particular case, one of the signals is infinitely long. So the result is also infinitely long. Okay, one more. U of t involved with t minus 1, u of t minus 1. Well, I recognize this as a delayed version of tu of t. So first, I'm going to compute u of t involved with tu of t. I don't know if that's in our table. It is. It looks like it's a more general form of it. Is the closest I get, is it 9? That looks most like what I have here. With m equal to 0 and transform pair 9. In the first column with capital M equal to 0, t to the 0 is going to be 1, so I'll have u of t convolved with, and then capital N is equal to 1. Right? So from transform pair 9, and what I say, n is equal to 0, m is equal to 1. Nope. M is equal to 0, n is equal to 1. I get, what's this? I get m factorial, n factorial over m plus n plus 1 factorial. That'll be 2 factorial, which is 2, times t to the m plus n plus 1, which is 2 u of t. As the result. Does everyone see that? A lot of substitutions I made there to apply transform 9. It's a generalized version of this though. Okay. Okay. So now I've got u of t convolved with t u of t. What's u of t divided, or I'm sorry, convolved with 2 u of t after it's been delayed by 1 second? That's just the shifting property. It's going to, the y of t is going to be a delayed version of this. It's going to be delayed by 1 second. So everywhere that t appears, and then that would be the result. Any questions about that? Okay, so this table's useful. Unfortunately, you can't use it to solve all problems. Let's go back and I want to torture you again with evaluating that convolution integral, because with a problem that is not in the table. So here, they ask us to find the convolution of t 0 less than t less than 1. And that's 0 for t greater than 1. And then h of t is u of t. So if you remember, the first thing you do is actually sketch both these functions as functions of tau. It's essentially a change of variables. X of tau. So it's 0 for all tau less than 0. And it's sine for equal to sine of pi tau for tau between 0 and 1. Sine of 0 is 0, sine of pi is 0. So this is just, x of t is just first hump of the sine wave signal. And then h of t h of tau looks like this. Now, and so this is actually, it's helpful in this interval. This is just sine of pi tau. That's not tau, that's 1. Now, if you remember, the next step is time reverse one of these. It doesn't matter which one you time reverse. My rule of thumb is time reverse the simplest one. To me, the simpler one here would be h of tau, but it doesn't really matter. So we time reverse, and this now becomes h of t minus tau as a function of tau. And then the origin then is shifted to t. And then the first figure I'm drawing is where t is negative. Now here's the mental picture. As t increases from minus infinity to infinity, this thing just moves to the right. And I'm constantly looking at the product of these two. As I've drawn it here, you see that the product is 0 everywhere. This is 0 for all tau greater than t. This is 0 for all tau less than 0 and greater than 1. But there's no overlapping region where they're both non-zero. So I can say, as long as t is negative, t less than 0, I get y of t is equal to 0. Now I'm going to change my picture here. And then now, have t in the region between 0 and 1. 0 is less than t, this is less than 1. And you might think, last time we had this triangular form, remember? And I had to break it down into region where we were before the peak of the triangle and after. That's because with that triangle, I had two different equations for those lines. Okay. Here, I've got the same equation that applies over that entire time interval. It's sine of pi t everywhere. So I don't have to break it down into before the peak and after the peak because I've got the same function describing x of tau in that interval. But I've got, my integral, it's the product of those two. So it's 1 times sine of pi tau d tau. But what are the limits on my interval? 0 to t. Does everyone see that? Because this is 0 for all tau less than 0. So multiplying whatever this is by that is 0. So I'm going to try it this way. What I'm going to get when I multiply these two out is that, right? And this is multiplying this by 1, I get that same thing. It's sine of pi t, sine of pi tau. But it's 0 for all tau less than 0 because this is 0, and it's 0 for all tau greater than t because this is 0. So my limits here are 0 and t. Integrate that, what we get? Minus 1 over pi. All right, derivative of cosine pi t would be minus sine. Pi sine, yeah, I think that's right. So minus 1 over pi. Evaluate this at t. I get cosine of pi t minus cosine of 0 is 1. So I can get rid of the minus sign by writing it like this. I'm going to give you a couple minutes. There's a third region here where t is greater than 1. So now I'm going to give you a couple minutes to find y of t in that region. This is probably one of the hardest topics we cover in this course, this little integral and getting these convolution results right. So if you're struggling with this, you're not the first. Okay, so I encourage you to get together in homework groups at a 6-foot spacing and work together, talk about how to go through these convolution results. So what's the product look like now? Looks like x of tau, right? Because this is 1 everywhere x of tau is non-zero. And so 1 times x of tau would just be x of tau. And then for tau greater than 1, this is 0, so it doesn't matter what's going on here, that would be 0. And then for tau less than 0, it's 0. So the product here is just sine of pi tau, d tau. And then what's the limits on my integration now? Where is the product function non-zero?
0 to 1.
0 to 1. Now, if you carry that integral out, you'll get 2 over pi. Okay, everyone get that? The reason I know you should get 2 over pi, it is a constant, right? Because as t increases, the picture doesn't change. I'm just always calculating the area of that hump. That never changes, even as t increases. So y of t is going to be a constant. And remember, I said these things have to line up at the transition points. So here at t equal to 1, I get 1 minus cosine of pi is minus 1. 1 minus a minus 1, or 2 over pi. So again, because I know this thing has to look like this then, 0, 1. It's got to be, for t less than 0, it's 0. And then in this region, it's for t between 0 and 1. I've got this result. At t equal to 0, I've got 1 minus 1, which is 0. So again, it matches. And then it's going to go up to 2 over pi, rather. 2 over pi minus cosine. Cosine is going down. I think this will do something like that. And reach 2 over pi at t equal to 1. And then it's going to be a constant forever. So this is what y of t would look like. Cosine in that range goes from 0, something like that. Picture may not be 100% accurate, but it looks something. But the endpoints are right. Okay? If you followed that, I think you're in pretty good shape with regard to convolution. Okay. And it's not an easy thing. Okay, I want to actually, we'll work through one of the problems on the project. We've got about 10 minutes. So, now you can use MATLAB Octave as a calculator and type in everything at the command line. Don't do that, okay? Because if you want to make changes, you have to go back and retype everything in. So what you do is you should always, in my opinion, except for maybe a one-line calculation, you should always create source files, and in Octave they're called scripts. So I'm going to actually here create an EE310 directory, and then from this little gear icon, I'm going to create a new file, and this is project 01. I think it's I think I'm going to look at problem 3 _ 03, and then scripts in Octave MATLAB should always have a .m file extension. So we do that, and then that will create the file for me. And then I can just double click on it and to go to the editor. Okay, so in the IDE here, I can flip back and forth between the editor and the command window using the tab. The tabs are at the bottom. I also have the full documentation is online. So like getting started, there's a lot of good stuff here. So while you're inside doing nothing this weekend, read through the documentation. So in this problem, we're asked basically to plot the sine wave. Okay. So what I recommend is don't hard code constants and use the defined variables. But we've got it. So we're asked to plot a cosine 2 pi f0t. So A is equal to 20. Now here, if I click on the little gear icon, it will automatically run the script. Now to see the output, I have to go back to the command window. Okay. I can also run the script here by just right-clicking and select run. I can also type it in, PR01 _ 03. Well, I have to click on the command window, PR01 _ 03. Notice it's the script name without the .m extension. And then another thing, students often try to use dashes in file names like PR01 -03. Don't do that. Octave and MATLAB interpret that as some variable minus the number 3. So don't use dashes in your file names. It interprets that as subtraction. So if you'll notice here, when I ran the script, it displayed that line, okay? F0 is equal to, what is the frequency? 10,000, I can enter that as just 10 E3. And then, again, I can save with Control S. Let me see if I can, is that a little better? I could just click on the run icon and it will automatically save the script and run it for me. Okay. Now, here, I don't want to see maybe every line of the script. If you end the line in a semicolon, that just suppresses the display. Now in C, like you have to have a semicolon at the end of every line. Okay. In Octave and MATLAB, it's optional and it has a completely different purpose. Okay. In Octave, it actually just it executes the line, it just doesn't echo it to the display. So if I run this now, I don't see any output. Now there is a workspace over here, is that what it's called? A workspace where I actually see A and F0 are defined. There is a clear function where I can clear all the variables, they're gone. I run the script. You'll see that the assignments are made, it's just that they're not echoed to the display. Okay, now, MATLAB and Octave are really designed to work with real data. They're not symbolic algebra applications. Like, I don't know if you, like Wolfram Alpha, I think maybe you guys have worked. What do you use in the calculus sequence now? Any Wolfram Alpha? Is that what you use primarily? They used to use a program called Derived. There's another program called Mathematica from Wolfram. There's another program called Maple. Octave and MATLAB are different. They're actually designed to work with numbers as opposed to doing symbolic algebra. Okay, so here, if I want to plot a function, like here it's a function of time, I actually have to define my time vector. Okay. And in this case, in part A, you're asked to plot this function over 10 periods with 12 samples per period. Okay. So there's a couple of different ways to do this. It says 120 elements exactly. What's the best way to do it? I'm not sure. I could calculate T0. Now I'm not going to calculate that on my calculator. It's, I'll have MATLAB do that for me. It's 1 over F0. And one way to generate my T vector, so I can generate the easiest way to generate vectors in MATLAB is using this colon notation, 1 colon 5, to generate a vector from 1 to 5. Or -5 colon 5, we'll go from -5 to 5. Or -3 colon 0.1 to 4, we'll go from -3 to 4 in steps of 0.1. So there's all kinds of ways to generate these vectors. Okay. So in this case, I want to go from 0, and this, the sample rate was given at 12 samples per period. Okay, so that would be T0 divided by 12. So I can go T0 divided by 12, and then I go out to 10 times T0. Okay. Now I'm going to just run this here. Okay. Again, I run this almost after every step. I'll see T0 kind of looks right, or my T vector, it goes from 0. If I scroll all the way back, it starts at 0, and it goes to 1 millisecond. Okay, not quite right, because if I look over here, there's actually 121 samples. That's I'm off by 1. Okay, it's like if I took 4 samples of a sine wave, I'd have one at 0, pi over 2, pi, 3 pi over 2. And then 4 samples of the next one would be, at 2 pi, so on and so forth. Here I got an extra sample right at the end. Okay. Doesn't really matter, in my opinion. You can go ahead and plot this. I'm not going to take off any points. If you wanted to fix that, I should really go from, I could do this, T0 over 12. And I might want to put parentheses around that. And then now if I run, that's pretty ugly. That's getting ugly. Okay. But now T has 120 elements in it. Typically the way I would do this is actually do it this way. Just generate a vector that goes from 0 to 119. And divide by 119. Divide by 120 and multiply by 10 times T0. 10 T0 is going to be a millisecond, so that'll go. I know now that if I run this, it's got 120 samples, and it'll go from 0 to almost 1 millisecond. Probably an even better way to do this is there's a function called linspace. And why is this so slow? Help is, the online documentation. Linspace, if I give it the starting and end points well, actually, that's not going to quite do what I want. That will go from 0 to 1 millisecond. It's not quite what I want either. Okay, so really quickly, because I'm out of time, this has got my time vector. I simply plot T and A times sine of 2 times I times F0 times t. So I pass it two vectors. I could call, well, we'll go ahead and run this. It's being really slow. It's probably because I'm running Zoom and doing the video capture. I hadn't thought about that. It's probably really slow. It's still down. So this should almost be instantaneous. And so I think I said you should get 10 full cycles of a sine wave here. The other way to do this is, define a new vector that's equal to 2 times pi times f0 times t, and then plot this. I'll get the same result. The t-axis is my horizontal axis, so again, it goes from 0 to 1 millisecond. If I leave that out of the plot function, it plots it versus the index of y, and so it'll go from 0 to 119. Okay. So it just has that axis scaled incorrectly. The last thing I'll show you, and this, because you can do time in seconds with x label. You can use the title function, the y label to label the y-axis, the title, put a title in the figure. So there's all kinds of things that you can do to play around with the grid. Now, this is now a normal text file, and you can cut and paste this into your total document or print it or whatever. Okay. So, but it's just a regular text file at this point. So now that I've got it working, then now I can include it in my results. I guess the other thing is the easiest way to include a plot like this I found is if you just hit Control Print Screen. Are you aware of that trick? It will, if this is my active window, Control Print Screen captures that window. And then now if I go into like Word, Octave has it. You can actually print out, capture the image directly, but usually with these monitors, they're high resolution enough. Then I can just paste that with the Control V right into my document. Oh, it's not Control. It is actually Alt Print Screen. I captured the entire, where's my, somehow I closed down my Word and I'm already over time. So have a good weekend. But Alt Print Screen and then you can paste it right into your document.